Hello and welcome once again to In Orbit. It is the podcast that explores how our activities in space are helping us down here on planet Earth. I'm Dallas Campbell, I'm your host. Today we're going to be exploring all things microgravity. Now, it's a topic we've covered before, but lots and lots of exciting things are happening, particularly when it comes to developing drugs in space. Enjoy the episode. Well, thank you very much for joining me in Orbit, Martin and William. It's great to see you. Great to have you with us. We're going to be talking a little bit about microgravity. But before we do that, I thought we'd just get a little introduction on you guys, who you are, what you do, why you're here. Martin.
No, thank you very much, Dallas. So I'm Martin Braddock. I'm founder and director of GENIXICONSULTIng. I've been working in the biopharma industry now for 29 years.
You don't look that old. Surely,
Thank you very much. Thank you. Formerly at AstraZeneca, before that at GlaxoSmithKline.
I thought you were going to say formerly an astronaut.
Oh, if only. Prior to that, I had an academic career at University of Oxford.
I've heard of that place. Yes.
And up the road, not far from where we are, I did my PhD work at the MRC's radiobiology unit.
Okay.
Which I just drove up to have a look at.
Radiobiology.
Shrouded in covers. So this was effectively looking at the effects of radiation on DNA structure and DNA damage.
Right, okay.
Which at that time, of course, was very topical. And maybe over the decades, it's become less topical. But now, again,
why was it topical in the decades?
It was topical really because this was at the almost at the start of the atomic energy boom worldwide.
Okay, right.
And of course, it had a lot of utility after the Chernobyl disaster and various other things.
Yeah.
As we'd expect with radiation as a source, there'll always be accidents, unfortunately, and we always need to have an understanding of what happens. And of course, radiation damage in space is just as topical.
I was about to say.
Ever.
Yeah. So you've been involved in pharmaceuticals and drug developments.
For
pretty much
long time.
Since the beginning of time.
Yes, since the beginning of time. Not quite, but not far off. Thank you, Dallas.
It's great to have you here and your expertise. We've got so much to talk about. William, from right here at the Satellite Applications Catapult, I think you have the opposite above us, actually.
Indeed, yeah.
We can hear you pacing about sometimes.
Yes. Well, thank you for having me. I'm William Birch, the Strategic Account Director for Space here at the Catapult. So that typically means that my job is to be friends with the space industry, to understand what they're doing, and to help drive economic growth, development, and R&D initiatives focusing on space.
That's a great job title, to be friends with the space industry. That's will you be my friend? I like that.
Indeed. And prior to the Catapult, my work was corporate finance focused on biomedical research and specifically longevity. So I have a keen interest in this subject.
Okay. Well, today we're going to talk a little bit about fun things we can do in microgravity. Well, when I say fun things, important things. There is a great revolution on the horizon, I suppose, about manufacture of things in microgravity. But we should clear up microgravity first, actually. What do we mean by microgravity? Why is the absence of something a useful thing, I suppose? So who wants to have a go at microgravity? Because I always get a bit confused about it.
So I think in its simplest form, so let's try and sort of break this down into simplest form. On Earth, we experience gravity, as we all know. And the reason that we experience gravity is because the Earth has mass, the Earth is spinning, that generates a gravitational force. And really there is no memory for any organism not having been in an environment where there's gravity.
Hang on, let's pause there. There's no memory of any organism.
Because gravity has always been there.
So it is one of
the Earth.
Okay.
So we have never experienced anything less than gravity. Are you with me so far?
I'm with you.
With you so
I'm
far.
pausing just because I just want it to sink in for a moment.
So our bodies have evolved, if you like, and grown up, as have other organisms, always in 1G. And when we go into space, despite the fact that we would still experience the Earth's gravitational pull, if you like, the gravitational field associated with it, Gravity decreases as we get further away from any planet that generates gravitational force by its mass and its rotation.
There isn't a point, and I think people get confused by this, where you suddenly go into space and gravity switches off.
No.
I think people think, well, look,
thing.
there are astronauts floating around, there must be no gravity, and that's a sort of a misnomer.
That's a misnomer. And the reason that microgravity, as in millionth of a G, is generated or is manifest on the International Space Station, for example, is that as a vehicle, it's rotating, it's orbiting the Earth in free fall.
Yes.
And that free fall motion is generating weightlessness, which is a consequence of the lack of gravitational force and therefore microgravity.
So it's not the lack of gravity, but it's the lack of effect of gravity.
Lack of effect of gravity.
It's the same microgravity as if you jumped out of a window
exactly
and didn't hit the ground.
In free fall, yeah.
It was a very high window.
It would be a very high window. And of course, we can generate that
Yes.
on what's called parabolic space flight.
Yes.
So if you're lucky enough or unlucky enough, depending on how you look at it, to have ever had the experience to have fallen in free fall, you would experience weightlessness, which is your shot at microgravity.
So the micro bit of microgravity, so we're in free fall, I get that. But there is still, when you say a millionth, there is still some effect.
There is still some effect.
But it's
very,
micro.
very tiny. Because we don't know, we've never experienced this type of thing before on Earth, our bodies respond very differently. So we don't have anything to push against. So in its simplest form, we don't have the need for the body to have the resistance that it has to certain forces.
Yeah.
And that has quite profound effects on bone mass, on muscle structure, on all sorts of things, how the heart beats and how our eyes see things, and you name it, it affects us.
Yeah. Happy with that, William? With that kind of micro, anything you want to add to that?
Yeah, so I think in this absence of microgravity, there are certain effects that are reduced. So sedimentation effects, convection effects,
yes,
and surface tension typically will take more precedent in space. Ergo, you'll get more spherical structures. There are some really interesting videos of watching fuel burn in a sphere in space. So those effects unlock some fundamental science that, as Martin says, we may not have awareness of.
I remember doing I can't remember what we were filming. We were filming something. I remember we were on top of the BBC television centre, and we had a candle and we attached a GoPro to it, and we dropped it off, and we could see the flame of the candle kind of become round, just to kind of show how flames behave in microgravity.
And the application thereof is to biopharma research and pharmaceuticals, is that you can get more uniform structures, you can get better cell cultures and more well-formed organoids. Yeah. But we'll get onto that now.
Well, let's get onto that. Is this so? Basically, we discovered the absence of gravity, this factor that, as you say, no organism has had any memory of. Was there a point we went, oh, crikey, this might be useful? Because we haven't been going to space very long, but presumably we'd be doing experiments with things like drop towers or parabolic flights. How long have we known this?
I think we've known this probably for at least 30 years, I would say. William, if you agree with that. So, and really where this has had some immediate application has been in the ability to form crystals.
Okay,
protein crystals.
Yeah, well, this is what I need is someone who's worked in the pharmaceutical industry for a long time to explain this to me, because I hear crystals as one of these things that I hear about when we talk about manufacturing and microgravity. Where do crystals and drugs fit together?
So in its simplest form, so let's just imagine we've found a new target, for want of a better word. We found something that's implicated in disease, and it's a protein, or almost certainly it would be a protein. Now, if we want to design drugs that typically inhibit that protein's activity, we would need to get a structure of that protein. And in most cases, the structure is derived by what we call X-ray crystallography.
Okay. And
to get that structure, we would need to have crystals.
Okay.
So crystal formation is really quite a key part of structural-based drug design.
So when you're doing drugs design on Earth, you're still thinking crystals.
We're still thinking
Okay,
crystals.
okay.
Now, there are new technologies that will help us with that, or will help actually compete a little bit with that, but they are complementary. So complementary technologies such as cryo-electron microscopy,
Crikey.
which is effectively the ability to have structural information without having crystals, can certainly help us in some cases, but not in all. And then, as we would expect with the artificial intelligence revolution, there is now a way of deriving a protein structure in silico on your computer. And that, I think, is certainly going to be a huge help to people. But again, it doesn't solve everybody's problem. Let's say we have our dream target, which is involved in, could be anything. Let's just say degenerative disease, Alzheimer's,
Okay.
one of the great unmet needs.
Yeah.
If we really want to try and understand structural-based drug design, we would probably throw everything at it. We would look at getting crystals on Earth. We would look at perhaps getting crystals in space. We would look at any of the in silico techniques that we have, and we would use cryo-electron microscopy.
Okay.
So getting crystal structures is still a key part of drug discovery.
Okay. So when you say crystals on Earth and crystals in space, let's stick with that. So what is the difference between crystals on Earth and crystals in space? Why is crystals in space more useful?
It's more useful because of what William just said, the ability of structures to segment in a more ordered way, because they're not constrained by gravity, helps get better quality crystals, grow larger crystals, which gives us better structural data.
Why is that? Why does absence of gravity or gravitational effects give you better crystals?
It simply allows sedimentation to occur at a slower rate and allows the crystal structure, if you like, to form in a more ordered way than it would do when it's being forced by gravity.
William, there's a word that you mentioned, which is convection. And I've heard that sort of thrown around a bit in terms of microgravity. And I think I don't quite understand what that means, or I understand what convection means, but the absence of convection gives you better production of crystals in microgravity. Is that right?
Yeah, indeed. And to go back to Martin's point with sedimentation, the major issue is on Earth with larger gravity. Larger parts, larger molecules will typically fall. Denser items will fall in a solution faster, which will affect the development of those crystals. Convection also has an effect here.
I mean, is it that you get less convection or no convection, or
less convection, and it's less prominent in space?
Right.
Ultimately, we can, as Martin says, create better, larger, more uniform crystals. Because it's not being weighed down by the effects of gravity.
Okay. How significant is this? I mean, is this kind of radically going to game change the way that we think about drug design? I mean, is it that revolutionary?
This could be a real game changer. Now, I've been around long enough.
Well, this is, yes.
Long enough to have worked in HIV research in the 1980s, 1990s. And at that time, there was a real desperation, as you can imagine, with this new virus on the horizon, causing a lot of deaths, particularly in low to middle income countries. Mm-hmm. Everybody was trying to understand how to find agents to inhibit HIV replication, or to stop the virus from multiplying. And one of the key targets in human immunodeficiency virus 1, HIV-1, is an enzyme called reverse transcriptase. And the reverse transcriptase X-ray structure was actually solved on Earth, but the studies conducted in space led to the development of what are called non-nucleoside reverse transcriptase inhibitors, analogues of those drugs, which most certainly have helped, I think, find us a way forward to enhance our understanding of the reverse transcriptase structure. Now, they didn't directly impact the discovery of the first drugs, but you can imagine now if we incorporated that microgravity study program into drug design at an earlier stage, it could possibly actually really start to drive the discovery and development of new drugs.
Wow.
So there is some precedent. There's also precedent with a molecule that's well publicized, which is Merck's Keytruda or pembrolizumab, where there have, I think, little doubt that space studies have helped in the development of new subcutaneous injections of that drug.
Well, presumably, actually, when you say subcutaneous injections, presumably that will have a radical effect, because suddenly drugs that you would need to do intravenously, which would involve going to hospital, suddenly people would be able to do things at home
much
on
more
their own.
acceptable.
And you would take away a lot of the burden on hospitals and the NHS and things like that.
Absolutely. I mean, you're absolutely right, Dallas. I mean, it's a potential game changer, I think, for patients who are going to receive these drugs, but also to accelerate the production of more patient-friendly drugs in the first place.
Yeah, that's really interesting.
But I think an important point to note, because ultimately our target is going to be commercial value. And having the ability to have patient-delivered drugs, subcutaneous drugs as opposed to IV, improves the ability for patients to continue taking drugs, the ease with which companies can sell those drugs, and ultimately increases the top level and the bottom line ultimately for those pharmaceutical companies.
So let's get this straight. So better drugs altogether because of the physical effects of microgravity, which in turn, well, more effective drugs, but also helps health systems, helps patients indirectly because they're easier to administer, et cetera, et cetera. Tell me, like, who's doing this at the moment? Like, where are we with all of this? Are drug companies making drugs up there in orbit? How are they getting them back down? Just give us a sense of the state of play.
This leads us on a little bit towards a microgravity workshop that was held here at the Satellite Applications Catapult last month.
This is the pharma workshop.
The pharma workshop, where we got together with people from the government, from UKRI, from academia, from pharma, from small companies, and actually started to think through, well, what are the blockers? Because right now, there is no clamour for large pharma to start making drugs in space and actually having dedicated microgravity slots within their drug discovery and drug development programs. So the question is, well, why is that happening? And I think, and perhaps I'm getting a little bit ahead of myself here, Dallas, but I think that the question comes down to thinking about the reliability of it, the reliability of actually doing studies in space to start off with. It's not perhaps the first thing that comes to mind. The cost of it, without actually even knowing what the cost is, I think that would be perhaps a little bit of a blocker to people who would think, well, it must be expensive. I don't actually know what it is, but it must be expensive.
Yes,
and then, of course, how fast can work be done that would help your discovery or development program?
So, okay, William, where are we with it? So are we still at very much sort of R&D phases, or are we developing drugs in space at the moment for production?
So this isn't a new phenomenon. The drug trials, drug development, drug discovery has been going on in the ISS for a very long time.
Yeah.
We've seen experiments from Eli Lilly, we've seen experiments from Merck, we've seen experiments from AstraZeneca. We've seen
these
experiments.
are all big drug companies. Just
correct. And we've even seen experiments slightly off topic from Adidas, looking at new foam creation for shoes.
Wait, new for shoes?
Correct.
This is the priorities, isn't it?
Yeah.
Shoes.
So there are lots of experiments. There's over 3,000 experiments have taken place
and
on the
semiconductors,
ISS.
presumably, and electronics,
semiconductors,
things like that as well. So it's not just drugs, but yeah.
Indeed. There are other ways of doing it. So there are companies like VADA. VADA has successfully sent up, orbited, and deorbited successfully with the payload intact several missions now. And they've developed ritonavir, which is an HIV drug, in space. They've deorbited it and they've delivered it to their client. So this is happening, and there are some new players out there in the market. So VAST and Axiom are looking at creating orbital space stations. So once the ISS is no longer functional.
All this R&D, is it all on the ISS? This is the only kind of platform where these trials are taking place.
The majority of the work is done in the ISS. There has been some work done with, as I said, VADA, they are a free flyer. So they are a separate spacecraft that goes up, orbits and deorbits successfully with a big heat shield to avoid breaking up in the atmosphere. There are plans to do likewise free flyers with the Exploration Company out of Europe, with Spaceforge out of the UK. They'll be looking at semiconductors, gallium nitride semiconductors, and there are plans for other platforms, as I said, like Axiom, like VAST. But yes, the vast majority of these experiments have been done on the ISS.
And what was this workshop, this pharma workshop? What was the point of it all? What was the
really the point of it was for us to come together and start thinking about, well, we know all this early phase work has been done.
Yeah.
What does it now take to make this into a product?
Yes.
And what does it take to make it into a routine part of drug discovery and drug development?
Yes.
Because, I mean, William's perfectly right. All of the studies that have been conducted on the ISS are very knowledge generating.
Yeah.
But they're not yet perhaps got to the point of value generation.
Well, presumably
in terms of
scale, there isn't an opportunity to scale this. We have the knowledge,
Not
but
yet.
how do you scale this up if all we have is the ISS?
And I think this is part of the challenge, which helps us think through then, well, this isn't just an R&D problem or challenge. It's a regulatory challenge too. We need regulators on our side to understand what the opportunity is. We need investors on our side prepared to take the risk, because, of course, any drug discovery or drug development program carries risk, and this will have the added risk of, if you like, trying to change the whole narrative for how drugs are developed and commercialized in future based on a space component. Which I think is very exciting, and I think it offers opportunity, but it's not a stroll in the park to be able to do it. The workshop that we had really highlighted the challenges, but also highlighted some potential solutions. And one of the areas that a number of us worked up and has been close to my heart for a while is actually the use of anti-resorptives.
You're going to have to translate that for me.
Okay, so if you're a patient with osteoporosis, you lose your bone mass. And this is as a consequence of you with an osteoporosis disease diagnosis on Earth losing bone mass. That's not too dissimilar from the bone mass that's lost when you're in microgravity with astronauts, simply because they don't need to use their bodies in the same way because there's no gravity or very little gravity to push against. So they start to lose bone mass, and the bone mass can be, I think it's between 1 and 1.5% per month. Which, despite nutrition and despite loading, is still a factor that is on the increase, as in the decline is still there. Now, drugs such as alendronate, which is one of the bisphosphonate groups of classes of drug, has shown benefit in many osteoporosis patients on Earth, so its benefit risk is well understood. And it has been shown to have benefit for astronauts in space. So the question would come is, why is it not approved for bone loss in space? And I think given that as a regulatory step towards helping regulators understand what the opportunity is, this case for astronauts, it's not so much in terms of a business opportunity, but it helps pave the way towards getting future drugs licensed for space. Is probably a good starting point, because we know it works in osteoporosis patients on Earth. It's got a very good benefit risk profile. There is the need for it for reducing bone loss in space. So what's it going to take to get it approved for bone loss in space? As
far as I know, it's notoriously difficult to get drugs approved on Earth. Seems to take a lot. I don't know. I'm ignorant in this, but my perception is it takes a long time. There is always a process that we have to go through, and of course that's to protect patients at the end of the day. But by and large, the process it's well defined, it's routine. It would normally take between 6 to 12 months to get a drug approved. And the regulators they're kind of on board with this idea of developing drugs off planet.
That, I think, is something that we need to work on. Because I'm not sure, and William, please disagree if you know more about this topic, but I don't think we've really had that conversation with the regulators regarding what it would take to have a drug approved for space use, let alone what it would take to produce a drug in space and have it licensed for use for patients on Earth.
Presumably the other barrier to all of this is cost. We sort of mentioned it earlier, but it's going to be, at the moment, presumably horrifically expensive to start developing drugs in orbit.
Yeah, so there is a slightly prohibitive nature to space. Even with falling launch costs, you're still looking at tens of thousands per kilo. And typically what's done on Earth is done in football field sized facilities.
Yes. Yeah.
Even a small lab in a university, that space, that mass in space would be significantly more expensive, not to mention that astronaut time is very expensive and it is limited. They have a limited time up there. They have lots of requirements on their time. And so automation and robotics is going to be a huge component of any manufacturing, any experimentation that we do in space. And it is the domain of companies that have been very successful in doing that, such as Redwire Space and others. So yes, there is a prohibitive nature to doing experimentation in space, which typically has a tertiary effect where we have to be very specific about the outcome that we want to reach. A problem with that, we're not doing fundamental science. There is some significant fundamental science that could be done on this subject that ultimately would never be done by the pharmaceutical companies because their defined outcome must result typically in an ROI. So there could be lots that we don't know about the body's mechanisms that could be learned from space, such as the expression of certain genes. In some of the cancer research that's been done in space, there are certain genes that aren't expressed in microgravity.
So pause there for a moment. Cancer treatments from who's doing that? Are there specific organizations who are specifically looking at cancer?
Of the 3,000 odd experiments that have taken place in space, there have been numerous studies into the effects of cancer.
Do you think that's one of the areas that developing drugs in space is going to help? Only because I say it because it's one of those diseases that touches everybody. Do you think that's going to help?
Potentially so. I don't think there's a prohibitive nature to those targets that we look at. As you mentioned earlier, Martin, Keytruda was a big success for Merck. And I think there'll be lots of opportunities for neurodegenerative therapeutics as well. There's been some fantastic research into interferon development in space also. Just
while we're talking about the workshop that you had here, I'm just interested in what the kind of roadmap at the end of it was. What was what did it lead to?
So the roadmap in the first instance, I think, and this is the most important part because this is the foundation, which is really now to start interrogating what I would call the drug discovery, development, commercialization value chain. Okay. So if you imagine you draw a long line from left to right, you can break it down into almost forensically segmented groups. And then really ask those tough questions. Well, does microgravity help with this? Yeah. Is there an ROI? Yeah. Or can we de-risk the process such that we will have confidence in generating an ROI? And then actually, can we develop use cases that people can get behind? Yeah. Because I think without that, we can have a regulatory framework, we can have a structure of collaboration, we can have lots of interested people. But I think without that, and of course investors, but without that, I think, solid set of use cases, then it starts to become, I think, a little bit more of an academic curiosity. And I think it would be unfair for it to remain an academic curiosity because there are some clear applications for us. I mean, I think one of the applications that, and we didn't have time to talk about this at the workshop in April, is the potential for 3D bioprinting. So I think probably most people are familiar with 3D printing. You can buy your own 3D printer now online if you want to and print little models and things. But the concept of 3D bioprinting, to be able to print perhaps sometime in future artificial skin, even small organs, even small, perhaps cartilaginous structures, makes you think about, well, is there the opportunity, futuristic that this may sound, to 3D print artificial skin and organs in space on demand? And that in its own right, makes you think, well, who would want that? Well, who would want that would be patients who can't get transplanted organs on Earth.
And can I just, in terms of 3D printing biomaterial in space, again, I've just got to ask, why do you need to be in space for that? Why can't you?
Well, again, it comes down to the lack of gravity and the organizational structure.
So it's just easier.
It's just easier.
And you get a better product?
And you would, in theory, get a better product.
Okay.
Yes. It's been tested in small experimental studies, but it's got quite a way to go before it becomes, I think, a serious exploit in terms of producing a product for people to use.
So we're not doing that yet. I'm interested as well because, we talked about the ISS, and that's basically the only kind of structure we have to do research into all of this. What infrastructure do we need for it to become a business where people do get a return on investment, where drug companies suddenly can start manufacturing at scale in orbit?
So I like the way that Axiom Space talk about their business. They're creating the real estate in space.
So they're the company that's building lots of architecture now for space. They're building space suits.
So they'll provide
the
warehouse. They'll provide the warehousing. They'll provide the unit in which you put your experimental devices or whatever, your manufacturing capability. Then you've got the element of what is inside it, what is conducting the experiment. So you have to consider a box that has automation, robotics, in order to conduct those experiments, those processes for you. And then you have to consider, what are those processes? You don't have a vast lab. You don't have the massive machinery that you would have in traditional pharmaceutical production. You have to miniaturize because cost is prohibitive when you have excessive mass. So there's quite a few areas that have to be developed, quite a few opportunities. You've got the real estate, you've got what's housing the experiment, what's conducting the experiment. You've then got the data. You've got a huge element of production and experimentation is going to be the fidelity of the data, the availability of the data. Can you timestamp it? Can you guarantee that quality assurance can be in the loop? If you talk about then manufacturing of drugs, you have already standards on Earth like GMP that have to be considered. How do you go about labeling? All of these things are massive considerations, but they are further down the line.
Where is this line? I'm kind of interested in what kind of timescale we have for all of this. And is this going to be beneficial to the UK particularly? It seems to be an area that we're thinking about a lot, and there's opportunity there. Is this all decades away or years away?
I think it's always a money question. If there's enough money, timelines are accelerated. If there isn't the availability of money and resource, then those timelines can't be accelerated. So should there be a massive investment in this from the UK government, we can accelerate those timelines.
Well, when I'm Prime Minister, that's it.
But I think, as with most things, we're not doing this on our own.
Well, that was the thing. But we're access to
we're
space.
Competing with every nation that wants to seize this opportunity. So that in its own right, I think, should drive a sense of urgency.
Well, presumably China and America are revolutionizing access to space recently.
No, they've made significant insights and continue to do so. And the ISS's Orbit Edge Accelerator program, which is offering funding for people to come up with ideas, I think is perhaps a model that maybe the UK should consider following, because we're a little bit reticent, I think, in perhaps encouraging this level of innovation and accepting of the risk that comes with it.
Do you think, when you're Prime Minister, do we need to be less risk averse and a little bit more adventurous in this?
I think any innovation comes with risk. So if we want to play it safe, then that's great. But then perhaps let's not expect innovation to the standard that it could be with the brain power that we have in the UK.
Thank you for coming in and talking about this. Let's just wave our magic wands, if we can, and propel ourselves a decade into the future? I mean, we live in a world of uncertainty is an understatement. But can you see a time in the future where drug development and health is going to be transformed by space?
I think in the first instance, I would like to see a time, and I think we will see that within a reasonably short period of time. So by that, I say 1 to 2 years. I would like to see microgravity accepted or not accepted, as the case may be, as a standard part of drug discovery and drug development.
Yeah.
Do we consider it or don't we consider it? If we consider it, what is a one-stop shop, if you like, to be able to get studies done in an effective way, in a reliable way, and at a price that we can afford? There will be an element of premium pricing because we have to pay for the access to space. But I think if we had that as our goal, that in its own right helps set the agenda for regulators to get behind and for suppliers to get behind, and also for investors to get behind, because they can see that there is a role for it, even if it's not to include it in drug discovery and drug development.
William, is it attracting investment? Or investors getting excited about the possibility of this? Is there gold and then the hills and in orbit?
There certainly is. We might not have seen quite such significant quantums as other areas of pharmaceutical development more generally and innovation in the UK. However, we are seeing significant money going into it. So SpaceForge just announced their successful raise of over $30 million. This is a fantastic step, albeit they are focused on material development in space.
Yes.
But I think that rising tide will raise all ships. As we push toward more development in material science, we can push towards more biopharma as well. So there's significant investment. There are UK companies looking at this, and it is a real opportunity.
Yeah, I think you're right. I can imagine a situation where you kind of look at the label of your product, whatever it is, your packet of drugs for whatever ailment you have, and it'll have made in space.
I mean, one thing that I've been working on with some colleagues of mine. So I'm a very keen, passionate astronomer, and give a lot of talks to amateur astronomy societies in the UK and Europe. And I've been working on something for some time, which has been on what it would take to manage injuries and wounding in space. Because as a consequence of lunar colonization and ultimately Martian colonization at some point in the future, accidents will happen. And where do we get the next generation of space medicines from? And in particular, when we think about the active pharmaceutical ingredient, the API of a space medicine tends to decrease faster than it does on Earth because of the environment that it's in. What do we do to produce medicines for somebody who's a colonist on Mars in, 30, 40, 50 years' time? Do we fly everything up from Earth, or do we actually make it in situ? And futuristic though this may be at present, the future isn't that far off perhaps for colonization of the moon, at least in the first instance, and then maybe Mars. So this is something that's very close to my heart, and that ties in quite nicely, of course, with what we've been discussing today, because it's a logical consequence perhaps of our early successes of producing medicines in space. Fantastic.
I was at the astronaut centre in Cologne, actually. They were
wonderful.
And they were testing out a moon stretcher for
Wonderful.
Exactly that. Just for in case someone trips up in Shackleton Crater or wherever they are.
It will happen, unfortunately.
Of course it will
happen.
Yeah. William, thank you very much indeed. Martin, thank you very much indeed for joining us today. And I'm going to be, as ever, watch this space.
Thank you.
Thank you.
To hear future episodes of In Orbit, be sure to subscribe on your favourite podcast app. And if you'd like to find out more about how space is empowering your industry, visit the Catapult website or join them on social media.